Quadratic equations, factoring, level 7. In the previous video, we learned how to factor quadratic trinomials of the form x squared plus bx plus c equals 0, where the coefficient of the quadratic term was equal to 1. Now we will change direction and focus on solving quadratic trinomials of the form ax squared plus bx plus c equals 0, where the coefficient of the quadratic term is greater than 1. There are two common ways to factor quadratic trinomials of this form. The first strategy is by trial and error. The second is by the method of decomposition and grouping. We will first cover factoring by trial and error. This method is similar to the method we used for quadratic trinomials where the coefficient of the quadratic term was equal to 1. Recall that if a quadratic trinomial of this form is indeed factorable over the integers, it would factor into two linear expressions of the form, the quantity x plus r times the quantity x plus s equals 0. For the case where the coefficient of the quadratic term is greater than 1, if the quadratic trinomial is indeed factorable over the integers, then it will factor into two linear expressions of the form, the quantity px plus r times the quantity qx plus s equals 0. To obtain further insight in the factoring process, let's go ahead and expand this expression by using the FOIL method. So first we find the product of the first terms, then the outer terms, followed by the inner terms, and finally the last terms. Next we add like terms and obtain the final expression pq times x squared plus the quantity ps plus rq times x plus rs equals 0. This final expression is in the form ax squared plus bx plus c equals 0, where a is equal to p times q, b is equal to the sum of p times s and r times q, and c is equal to r times s. This expression gives us an insight on how to factor quadratic trinomials, where the constant in the quadratic term is greater than 1. According to this expression, we need to find factors p and q whose product yields the quadratic term a. We also need to find factors r and s whose product yields the constant term c. And lastly, factors ps and rq whose sum equals the linear term b. Notice that p times s is the coefficient of the outer terms in the factored expression, and r times q is the coefficient of the inner terms of the factored expression. With this in mind, let's go over an example to illustrate this procedure. We will first illustrate the trial and error method. Solve the equation 3x squared plus 7x plus 2 equals 0. Alright, first thing I want you to notice is that we are dealing with a quadratic trinomial, where the coefficient in the quadratic term is greater than 1. It's very important that you are able to distinguish quadratic trinomials of this form, since the procedure to factor them is completely different, depending whether the coefficient in the quadratic term is 1 or greater than 1. In this case, the coefficient is greater than 1, so the factors of the quadratic trinomial will have the following form, granted that it's factorable over the integers. For the case when a is greater than 1, we're going to find the factors by trial and error. This is similar to the way we factored quadratic trinomials in the previous videos, when the coefficient in the constant term was equal to 1. In this case, we're going to have a couple of tables. The first table will list the factors of the quadratic term, in other words, our p and q. The next table will list the factors of the constant term, in this case, r and s. So let's start with the factors of a. The coefficient in the quadratic term is 3, so the factors of 3 are 1 and 3. These two factors pretty much covers all of them. Next, let's find the factors of the constant term c. In this case, we're looking for the factors of 2. Notice that both the linear term and constant term are positive. This means that we are solely looking for positive factors of the constant term, similar to the way we factored quadratic trinomials when the coefficient in the quadratic term was equal to 1. So the factors of 2 are 1 and 2. And that also covers all of the potential factors. Having found the potential values for p, q, r, and s, we go ahead and create a third table with the possible factorizations of the quadratic trinomial, and a second column with the sum of the products of the inner and outer terms. We generate this list by first listing all possible factorizations with the given values of p, q, r, and s. The best way to do this is to first start with the values of p and q and systematically generate all the possible combinations that include r and s by switching them. The first potential factorization is the quantity x plus 1 times the quantity 3x plus 2. The second possible factorization is obtained by keeping the factors for p and q and switching r and s in each factor, as follows. Doing that, we obtain the quantity x plus 2 times the quantity 3x plus 1. The final step is to find the inner and outer products of each potential factor and add them. The purpose of this step is to match the linear term of the quadratic equation. So the first factor's outer terms yields 2x, and the inner terms yields 3x. And combining like terms, we obtain 5x. For the second factor, the outer terms yields x, and the inner terms yields 6x. Combining like terms, we obtain 7x. And jackpot, this is the linear term we want to obtain, since it matches the linear term of the quadratic trinomial we want to factor. Having matched the linear term, we have successfully factored the quadratic trinomial. The factored form is the quantity x plus 2 times the quantity 3x plus 1. Next, we apply the zero product property to each factor and solve for x. Doing that, we obtain x equals negative 2 as one solution, and x equals negative 1/3 as a second solution. For the most part, many students forget that when you're dealing with a quadratic trinomial where the coefficient of the quadratic term is greater than 1, requires a slightly different procedure to successfully factor it. Not only do we need to find the factors of the constant term c, but also the factors of the quadratic term a. Personally, I try to avoid the trial and error method when factoring quadratic trinomials, mainly because it requires you to systematically test a number of potential factors. For those students who are good at guessing and are naturally good with number sense, then this method is for you. We can also factor this quadratic trinomial by the method of decomposition and grouping. This method is more procedural and has a well-defined built-in algorithm that many students like to use. So let's go ahead and solve the same quadratic trinomial by the method of decomposition and grouping. Solve the equation 3x squared plus 7x plus 2 equals 0. The first step is to always write the quadratic equation in standard form, with the powers of the terms in descending order, and 0 on one side of the equation. So we see that this has been taken care of for us. The next step of this method is to take the coefficient of the quadratic term a and multiply it by the constant term c. Doing that, we obtain 3 times 2, which signifies to 6. Subsequently, we want to find two factors of 6 that add up to the coefficients of the middle term. Keep in mind that we are looking for two positive factors, since the sign on the linear term and constant term are both positive. Like always, let's systematically list the pairs of factors until we generate all possibilities. This is analogous to the way we listed pairs when we were factoring quadratic trinomials where the coefficient of the quadratic term was equal to 1. So the first pair is 1 and 6, and the second pair is 3 and 2. Next, we want to find the sum of each pair. So the first pair add up to 7, and the second pair add up to 5. Having found the sums, we scan the list looking for the sum that matches the coefficient of the linear term. We see that the factors in the first row satisfy these requirements. This process is very reminiscent to the method we used to solve quadratic trinomials where the coefficient of the quadratic term was equal to 1. This is another reason why I prefer this method. One of the steps is similar to something that I have done before. The next step is where the decomposition part of the method occurs. We're going to decompose the linear term 7x into an equivalent expression using the factors that were obtained from the product of the coefficients a and c of the quadratic trinomial, in this case 1 and 6. So we decompose 7x into 1x plus 6x. Notice that 1x plus 6x signifies to 7x. So in theory, we still have an equivalent equation. All we did was to decompose it into two other terms by using the factors of 6. Next up is the grouping part of the method. We're going to group together two terms. You might ask yourself, does it matter which two terms we group? The answer to that question is, as long as you group a decomposed term, 1x or 6x, with a non-decomposed term, 3x squared or 2, everything will work out. So I'm going to group 3x squared plus x and 6x plus 2, as follows. Next, we need to factor out the GCF for each grouping. In the first group, the GCF is x, so we factor that out and leave behind the quantity 3x plus 1. In the second grouping, the GCF is 2, so we factor that out and leave behind the quantity 3x plus 1. Notice that we have the quantity 3x plus 1 as a common factor from both groupings. This is a key step in the process. You always want to end up with a common factor in each grouping. If this was not the case, you made it an error when you were factoring the GCF from each group in the previous step. The final step is once again to factor out the GCF, in this case the quantity 3x plus 1, as follows. Then we leave behind the quantity x plus 2. If you're still confused of what just happened, consider the following equivalent expression. If I were to replace the quantity 3x plus 1 with the variable y, and ask you to factor out the GCF from this expression, you would most likely notice that both terms contain the variable y in common. So you naturally factor out the variable y, and leave behind the quantity x plus 2. And the expression will look like this. Y times the quantity x plus 2. Now, in our example, y is equal to the quantity 3x plus 1, and will look like this. In the end, you're factoring out a common factor which happens to be a binomial. It's no different than that of a monomial. The last step is to apply the zero product property to each factor and solve for x, obtaining x equals negative 2 as one solution and x equals negative 1/3 as a second solution. Alright, in our next video we will continue going over various examples illustrating the way to factor quadratic trinomials where the coefficient of the quadratic term is greater than 1.